Hello everyone, my name is Anna Rinaudo and I'm a PhD student at the University of Genova. In this contribution I will present our work on next-to-leading log resummation for the case study of Higgs-induced DIS, a process similar to the usual deep inelastic scattering, but instead of being initiated by a photon, it's initiated by a Higgs boson. Let's start with some introduction and motivation for our work. The main tool used in particle physics to make theoretical prediction is the perturbation theory. In particular, for the energy scales relevant at LHC, the most important contribution came from strong interaction, and so we are particularly interested in perturbative QCD. So we write our observable as a series expansion in the coupling constant with some coefficient Cn. The key point of this formalism is that this product must be small, and then alpha has to be small enough, but also the coefficient has to be not divergent. And this is particularly relevant in QCD because thanks to the group renormalization group equation, alpha is small, but is not that small. And so it happens that this product is of order 1. So let's see more in detail what is the behavior of this coefficient Cn. One finds that in Cn there are these logarithmic contribution, where x is some ratio of the scales involved in the process. And as you see, this is dangerous in two regions of the phase space. The first is when x is close to 1, and this is called the large x limit or the threshold limit. And the other region is when x goes to 0, and this corresponds to the high energy limit, and is the one we are interested in. When one looks closer the extractor of this coefficient in the small x region, one sees that there are different power of logarithm that contributes. And in particular, the one with the same power of the coupling constant is the leading one, and the other are suppressed by power of the alpha. But if one wants to make a precise prediction, one in principle has to include also this subleading term. And they are called the leading logarithm term and next to leading logarithm term, and so on and so forth. This is a severe problem because the presence of these terms spoils the convergence of the perturbative series, and so the theoretical predictions are no longer reliable. The solution of this problem is that we have to find out the L-order structure of this logarithmic term and then write them as a series expansion and sum it. And this process is called resummation. One can ask how much the resummation of this small x contribution can improve the theoretical prediction. One can compare the resummed result with some experimental data. In this case, we have the as observable the longitudinal structure function for the DIS, and we have the dot that represents the data from ERA. And we have that the green dashes are the prediction of next to leading order prediction without resummation at different value of x, and the purple dashes are the next to leading order prediction with next to leading order resummation. And we see that the resummed result describes aware better the experimental data. Now one can ask how does this small x resummation work in practice. The first thing that you have to know is that the resummation always relies on some factorization property, and so we will look for some factorization property of our observable. I will also use the Mellin transform. Essentially, instead of look at our observable in the x space, we will look at them in the n space. And this is useful because we will map the log x in two poles in 1 over n. As I said, we want to exploit some factorization properties. The first is the Collinear factorization theorem that says that we can write our observable, like a cross-section, as a product in a Mellin space of a part that is the coefficient function, that is process dependent, and a part that instead is process independent and encodes the probability of finding a specific parton of a specific momentum inside the proton, for example. At low x, we find that the problematic terms are both in the coefficient function and in the parton distribution function. This means that we need a technique that allows us to resum both of them. The goal of our work is to give a method to resum logarithm in the coefficient function up to next to leading logarithm. To do so, we can exploit another factorization property, the high-energy factorization theorem. This holds also away from the collinear limit in the high-energy region, and one can prove that in this region the main contribution is given by the gluon. Then we can write our cross-section as this convolution, where we have the off-shell coefficient function, that is the coefficient function of the process, but computed with the incoming gluon off-shell. And to give the off-shellness to the gluon, we assign it a transverse part to its momentum. And then we have the unintegrated PDF. The unintegrated PDF is linked to the PDF, the one we were discussing in the previous slide, by means of this evolution factor u. Comparing this expression with the one in the previous slide, one can easily find out that in the region when both these two theorems holds, one can write the coefficient function like this convolution. And this is really the formula that allows us to resum the logarithm in the coefficient function. In fact, this evolution factor u is process independent, and one can compute it at the required logarithmic accuracy. And the off-shell coefficient function instead is process dependent. We can compute it at some order in alpha s, but the really important thing is that it doesn't contain any small x singularity. To implement this procedure at next to leading log, we decided to start to study it in a simple case, and we choose as a case study the Higgs-induced DIS. We choose this process because it's the simplest process initiated by gluon, and for this reason here the small x resummation is relevant. To keep things as simple as possible, we choose to work in a pure gluon theory, and so we put nf equal to 0. Because of the fact that the Higgs doesn't directly couple with the gluon, we had to use this effective vertex. And then we want to compute the off-shell coefficient function, and so we had to assign to k1, that is the momentum of the incoming gluon, a virtuality, and we did it in this way. As I said before, we want to compute the resummed coefficient function up to next to leading log, and so we have to compute the off-shell coefficient function at one loop. A key point to achieve small x resummation is the fact that in the off-shell coefficient function there aren't logarithm of x. And one can prove that this happens only if we work in a physical gauge. And for this reason we choose to work in axial gauge. As you can imagine, working in axial gauge instead of Feynman gauge can bring some complication. The first is the fact that the number of terms involved in our calculation is higher. In fact, every time in your graph you have the propagator of a gluon, you have to write it down with this expression, where in addition of the usual Feynman gauge term, you have also this contribution. And this means that every time you have a propagator of a gluon, you have twice the terms. But the most serious problem is the fact that working in axial gauge, one has to deal with non-covariant integrals of this form, where the fact that are non-covariant is due to this denominator. This was quite a tricky point in our calculation, but after some time we have learned how to deal with integrals of this form. So, where are we? I recall you that we want to compute the resummed coefficient function using this formula, and we are the final stage of the calculation for this important ingredient, that is the off-shell one-loop coefficient function for this process. As I said before, the main issues we found were due to the fact that we chose to do this calculation in axial gauge. Then there is the evolution factor U that I didn't have time to discuss during this talk, but I remind you that it is process independent, and we know it up to next to leading log accuracy. Then what is left to do is put these two things together and do this integration, and finally we will get the resummed coefficient function for this process. Having done this, we could generalize this procedure to other processes, like the usual DIS initiated by a photon. And this is particularly relevant because it can be used to fit the PDFs. And with this, I conclude, and I thank you very much for your attention.